Example 7, and these are the type of problems that you're going to have today. A little bit of them is still examining graphs of exponential functions, which is the stuff that you should be pretty decent at by now. Just remember inside, outside for your shifts. Up, outside is your vertical shifts, inside is your horizontal. You still have the expansion factor of A, the environmental or the natural constant of E. But more or less, we're going to be using exponential growth and decay. So if you remember those two equations for exponential growth, n, which is the number after so many years, is equal to n of 0, which is the initial population, times the quantity of 1 plus r to the t. Okay, this would be growth because we're adding r, so we're growing exponentially, so 1 plus r. Exponential decay, it's the same equation where n of 0 is your initial population, but it'll be 1 minus r to the t, and t is always represented in years. So when we're talking about exponential modeling, we're going to be given certain data points, and we're going to be able to plug this in to be able to solve for r. Okay, that's the main goal that we have here. And it should be pretty simple. Nothing too terrible to just test your algebraic skill, but if you follow the rules of solving equations, it's pretty logical, it's pretty simple. Just remember to solve equations, we reverse PEMDAS. So our example, for example 7, says deer. Table shows the population growth of a deer in a forest, from 2000 to 2010. If a number of deer is increasing at an exponential rate, identify the rate of increase and write an exponential equation to model the situation. And we're given the deer population in 2000 was 125 deer. The deer population in 2010 was 264. So we want to take this information and we want to plug it into our exponential growth. Okay, so exponential growth is 1 plus r. So what I'm going to do is I'm going to take the amount of deer that was in 2010, and I'm going to set that equal to n. Okay, why am I setting that equal to n? Because it's not the initial population I'm doing. That's the number of after 10 years. Okay, so 264 is going to be equal to n. The amount of deer in 2000 was 125. Okay, then I still have my 1 plus r. And remember, I'm trying to solve for r. I'm going to carry that to the 10th power. And I have this equation, and I'm trying to solve it for r. So like I said, we have to reverse PEMDAS. Remember, PEMDAS, we would start with parentheses, then our exponents, and multiplication, division left to right, addition and subtraction left to right. So I'm going to reverse that. So I take care of my parentheses absolutely last. The first thing I want to do is I want to isolate those parentheses. So I have to divide by 125 on both sides first. Okay, because if I'm reversing PEMDAS, it would look like this. Where I take care of subtraction and addition first, multiplication and division, then my exponents, then the parentheses. But in this case, there is no subtraction and addition. So I just skip it, go on to handle my multiplication. So divide by 125 on both sides. Okay, so now what I'm left with is 264 divided by the quantity of 125 is equal to 1 plus r to the 10th power. Okay, so now I've got to get rid of my exponent. So I'm going to take it to the 10th root. Okay, so the 10th root of 264 over 125 is equal to 1 plus r. Okay, now I can subtract so that r is equal to the 10th root of 264 over 125 minus 1. Okay, now I'm going to plug that into a calculator. On your calculators, okay, if I pull up my meta calculator, I'll do it there to make sure. That way you can see it. You'll notice that there isn't a 10th root button. Okay, but if you remember from the powers of rational exponents, having the 10th root is really taking something to the 10th power. Okay, so I'm going to use parentheses just to make sure everything comes out right. In 264 divided by 125. And I'm going to take that to the power 1 divided by 10. That's the exponential way to write the 10th root. Okay, at this point I get 1.0776.2. Okay, so now I'm going to minus 1 at the end of it. And you can see I'm left with 0.0776. Okay, rounding up. So my R value is equal to 0.0776. Okay, and the hardest part is really just remembering that I can take the 10th root by raising it to the 10th power. Okay, that goes way back into the first semester, where if you had a square root, it's really taking that item and putting it to the half power. Okay, but we've covered stuff like that. But now we got to answer our question. Okay, identify the rate of increase, which we did. It's 0.0776. And write an exponential equation to model this situation. So my model when it's all said and done is going to be n is equal to 125, because that's still my initial population, times the quantity of 1 plus 0.0776 to the t. Okay, if I plug that in, if I were to graph that and plug in 10 for t, I should end up with 264. Okay, so that's step one, is getting the equation that models it. Show you the book's version. It's always fun to see this because you'll know if I make a mistake. Okay, so we've let n of t represent the deer population 10 years after t. So n of 0 is 125 at the time t is 10, 2010. So there's our exponential growth formula. There we're plugging it in. We divide. We take the 10th root and we subtract 1. Oh, they took it to the third. Those jerks. I went to 0.0776. So if I were to round that up, it could be 0.078. So 3 places will be enough to handle this. So our rate, that's the percentage value of this. So 7.8% in decimal form is 0.078. Our equation is equal to 125, 1 times 1.078 to the t. If you look, the only thing I didn't do, I didn't round this because this will round up. Okay, and then they just add it to 1. So I'll adopt theirs. But it's the same thing. They just didn't break it out. 1 plus. Okay, so I added 1. So that's the equation we're going to be working with. That's our modeling equation. Okay, but there's always a follow-up question. Okay, the table shows the population growth of the deer in forest from 2000 to 2010. Use your model to predict how many years it'll take for the number of deer to reach 500. So here, the easiest way to handle this is to pull up a graph. Okay, in the first equation we're going to graph. So I'm going to do this on Desmos. Let me add myself a tab. And expand it back. Okay, perfect. Okay, because I have a graphing equation and I want to know where it's 500. So the first equation I'm going to put in is my modeling equation. So 125 times the quantity of 1.078. Yeah. To the power of x. Okay, because that's my modeling equation. Why did it not take it? Do I got to hit y equals? Why are you not working, Desmos? Y equals 125. See if it'll graph that. That's way up here. So much easier to do this on a graphing calculator. Oh, speaking of that, if you're a junior and you're interested in having a graphing calculator because you do not have one of your own, then you can let the school know or let me know, and I'll do my best to get you one checked out this week. We want to get them sooner rather than later. Okay, let's try this again. 125, quantity of 1.078. See if it takes it this way. Power x entrada. Why are you not taking it? Still not taking it. Oh, there it is. Okay. I was just looking too close. Okay, so just be wary of your scale. I should have been smart enough to realize that it's going to be 125 as my intercept. Just poor planning. And then on the second equation, I'm going to enter y equals 500 because that's the amount of deer that I want to know. Okay, so I'm going to go up to where 500 is. I'm going to click so I can see this inner point intersection that says 18.457. Remember, that represents the amount of years. So 18.457 years gives me the quantity of 500. And that's after how many years it'll hit 500. So in roughly 18 and a half years, so in 2018, around the month of June or July, my deer population will hit 500. So find the intersection, which is about 18.5. That's them. You can do it on Desmos. Just don't make the mistake that I just did. Realize where you're going to cross the y-axis and don't drive yourself nuts that way. Okay, so since T is the number of years after 2000, so plus 18 is 2018. Like I said, it's a half a year, so roughly around the year 2018 in the month of June or July. So approximately 18 years would be our answer. Okay, we'll do one more. So use the data and assume that the population is growing exponentially. Identify the rate of growth and write an exponential equation. So from 2005, we had 4.5. It's in hundreds, so 450 rabbits. And then 2010, we had 660. So I can use the decimal forms and not have to use big numbers. But remember, it's population growth because the year after is greater. So first step, fill out my growth equation, and then I'm going to solve it for R. So N is 6.6 is equal to, my initial population is 4.5. 1 plus R to the 5th power. Yep, because it's 5 years. Okay, and then I begin to solve it for R. So first I divide. So divide both sides by 4.5. So 6.6 divided by 4.5 is equal to 1 plus r to the fifth power. Okay, then I take the fifth root. So the fifth root, 6.6 divided by 4.5 is equal to 1 plus r. Then I subtract 1. So that r is equal to the fifth root of 6.6 divided by 4.5 minus 1. Okay, and then I plug that into my calculator, my meta calculator. Pull it up. Here we go. That's going to take care of everything that I need. Once again, use your parentheses, 6.6 divided by 4.5 to the power of 1 divided by 5 because it's the fifth root. Oh, come on, Mr. Burns. Yeah, I get it. It's a special character. There we go. Minus 1. You can see my growth factor is 0.0796. So if I round that up, that's going to be roughly 8%. 0.0796. Rounded up 3, can't round up 9, so that turns into 0.08%. Okay, so 8% is my growth rate. And then I write my modeling equation. By taking that information so that n is equal to 4.5 times 1.08 to the t. So that should be the answer to my first question. So you can eliminate certain answers, like they all have 8% as the growth rate. But you can see this 0.92, that's exponential decay. If you think about it logically, if you take a decimal and multiply it by itself, it just gets smaller and smaller and smaller. So that's what turns it into exponential decay. Sorry, I forgot to send in my lunch order. Dang it. So we know it can't be A or B, so it has to be between C and D. Looks like it's going to be D here. Perfect. Now the next question, use the data in the table and assume that the population is growing exponentially. Use your model to predict in which year the rabbit population will surpass 850. So realize we're using decimals because the data presented to us was in hundreds. So really we're looking for 8.5. So I'm going to go to Desmos again. Hopefully I won't butcher it this time. Change this to y equals 8.5. Change around my equation. That's 1.08. That's 4.5. See, my intersection is at 8.26485, so that's roughly at 8 years. So approximately 8 years, and it began in 2005, so 2013. Okay, that's the type of stuff that you're going to be doing today. Your modeling equations, like I said, it's not really the hardest thing in the world. It's just more plugging it in